Good morning. Welcome to this first morning talk, which I gave a kind of a provocative title, is Long-Term Planning Socialism. So I hope there are not too many politicians in the room, because political decisions are of the day, whereas long-term planning, people probably sometimes do not like to think about so much. But in this presentation, I want to advocate very strongly to think more, to think further ahead, and to calculate more. If you do so, and then you are at some point forced to talk about we need to have a master plan to somehow follow a route of no regret. And once you use that term, master plan, then the free market philosophers are at your heels. And they say the free market is going to solve it all. And then I like to ask them back, would the free market have been able to bring this unit onto the moon? Or does it need more careful planning? And actually what I think is that the energy system transformation that we are facing now is something that is much more challenging than just bringing this vehicle to the surface of the moon. This is technically more complicated, the system is more complex, and the relevance for life and well-being on this planet is much more dependent on that. So I want to do two things. First of all, I want to motivate my talk by showing some of the mistakes that had already been made in our German system transformation due to poor planning. And once we are through this motivation, I want to give you a flavor of how a long-term planning theorist works, so what the methodologies are. And I think we all agree that we cannot foresee the future, but what we can do is we can study scenarios and we can also think about parametric dependencies. So how does one quantity depend on the other? And these conceptual works that help us to steer our decisions. So I present four of these flaws that I already realized in our transformation. And one of the first questions you have to ask yourself is, how large is the energy consumption really? And when we started this off in Germany, let's say 25 years back, it was all a discussion on the electric sector. And our electricity consumption is some 550 terawatt hours per year. But then, sometime later, we understood that we have to integrate the heat sector, because that is, in fact, in Germany, the one sector that emits most of the CO2, 1,500 terawatt hours energy equivalent. So we said we have to include this, and we raised this figure to over 800 terawatt hours. Then, again, some 5 years later, or 3 years later for that, you said, no, the mobility sector is a strong emitter too. And then we raised the target figure to 1,000 terawatt hours. And now we understand there's also air traffic and shipment, and there's also the chemistry sector. Thank you. And we are raising this figure again. So, but all of that could have been seen beforehand. It's not that accidentally you understand that there are all these other things. If from the beginning you start to think we have to somehow decarbonize the whole energy sector, then you start to think all of that. And you confront yourself with a number that is 3 times higher, and of course that has a lot of implications of how you steer the whole transformation. Here's another one, and I think this one is still very actual. We, as you learned yesterday, we have now put away the nuclear power. It is fading out by the 2020s. And now we are discussing to fade out coal as well. But I think we will come into a very severe problem if we really do so. This is all the question of, and we had it yesterday, how large should the backup power be? And this is a thing you have to really deeply think about, and how to gauge this. If we are talking about the backup power, we are talking about something like the safety belt in a car. The safety belt you do not gauge by calculating average figures of accidents or so. The way to gauge that is completely differently. Yeah? So just a simple argument, I would say this safety belt of the energy system should be gauged with the allowable minimum consumption power that you want in your system. And what it concretely means in I think all of the world's energy systems is that we have to have a backup power plant fleet in place that is gas-fired, because in the end you can substitute the gas by synthesized gas and meet the CO2 targets. And you can gradually move from coal-fired power plants, there's lots of the infrastructure that will survive, and substitute it by gas. I showed this slide yesterday just to indicate that here's an alternative. Do you go into the direction of combined heat and power because you say that the fuel efficiency is much better if you also make heat out of your fuel? Or do you miss out on the counter-electric load? And in a country that needs a lot of heating, like in Germany in wintertime, we must electrify this completely. We have to have the heat pump in place, not only because it's more efficient, but also because it is creating this counter load. Because I told you yesterday that the electric power that is latent in the system is a factor 3 or 5 higher than what we have as a load today. So we have to create new, let's say, new dump loads, stupid loads that are very shiftable. And these come from the heat sector and from the mobility sector, where battery charging or heating, if you have sufficient heat storage, is something that you can shift around. And here's the fourth one. I also showed this yesterday. This is about somehow assessing market dynamics. If you have any regulation that puts the interest rate of your renewable investment above a certain threshold, then it's very likely that the system explodes in some way. So you have to have a control mechanism. I would say this is much harder than these technical issues because here you are judging an economical system. So we opened this box, let's say, and then within just 3 years, we had this exploding installation curve. And then we ramped it down again, which was two mistakes in a short time series. So again, if you know where you are going, what your, let's say, asymptotic installation rate is, you can devise a much better plan. So I hope this suffices as a motivation. Now I just, as I said, want to give you a little flavor of how long-term planning works. So first of all, we have to understand that if we're going from a conventional system, we have the storage, if you want, we have it pre-existing. It's the natural storage of the fossil fuels, including uranium. And we have a conversion unit where the generation follows the load. If we go over to the renewable system, what we are missing out is now this pre-existing storage of energy. We have volatile energy coming in, and at some times we have to balance the system by something that we have stored technically. So the technical storage here is the very different invention that was not present here, not on that scale. So what we are introducing are the technical design quantities. The first is the mixture ratio between mostly wind and solar. The next is the absolute value of your installation, which has to conform to the end energy target that I talked about before, the size of the storage, the charging power of the storage, and the discharging power of the storage. So there are 4, let's say, new parameters, design parameters of the system. And as with the mistakes that we made in long-term planning, there are also economical design quantities. So that is the rate of change. How quickly do you want to go from the status as is to the future state? That's also a very interesting question. It has also social implications and economical implications, and you have to think about it. And another interesting one is, in Germany, the leading industry is the automobile industry. We could say that the leading industry for the next 2 decades could be the energy infrastructure-related industry, and that would mean we could put more emphasis on the energy sector. In that case, let's say the ratio of the value creation of energy with respect to all the rest of the economy could be larger, or it could remain the same, or in the end could even get lower. So it's another important design parameter. So now what is at the core of long-term planning? It is in fact calculating the cost, and there are 2 important parameters. These are the specific cost per power summed up over all the investment, and you want to minimize that. And all of that works under boundary condition. The boundary condition is that at all times you feed the supply so that you keep the energy balance. But in fact, the cost term, or the sum of costs, is a little more complicated. It includes a power-related cost and energy-related. For example, the tank of a storage is energy-related. So these are the parameters you have to think about. If you think about the loads, or the final target, you have to somehow prognose the population growth. In India, I would say the energy consumption per capita will rise, whereas in Germany we try to saturate this. But I think you're not in the saturation level, so that makes the target calculation more challenging in India. And then with respect to generation, I think that's an easy one, yeah, because I hope so that this cosmic, astronomical, and also the atmospheric signals do not change so much, even given climate change. Then the storage size very much depends on the characteristics of the residuum signals. So let's say the pauses in energy generation determine the size of the tank. And then on the side of the cost, specific cost, the factors C here, it is the price development of technologies, also of course the price development of the fossil energies as long as you need them along this path, and also a possible price development for CO2. So the question I put here as a title on the slide is which of these quantities are harder and which are easier to predict? So if you now go into more involved calculations to somehow come to parametric dependencies, you can separate the cost issue from the boundary condition. And if you do this job correctly, you can bring the boundary condition in a very compact form. This is indicated here on the right. Dependence of the generation power on the storage power. So you can imagine if you make your storage larger, you keep more of your generation, you don't throw so much away, and then therefore the generation can be smaller. You see that in the blue curves. Please note here that this cutting of these blue curves is artificial. In fact, these blue curves go to infinity. So what it means here that to the right side of the blue curves, you are in what can be realized, a technical realizable system, and to the left side is those systems where generation and storage is too small and there will be no feasible system. And the parameter of this ensemble is the return efficiency of the storage. So if you have a more efficient storage, of course, this curve is lower. And realistically, for this large storages that you are talking about, the so-called return efficiency, so energy in and energy out of the storage, is between 30 and 40%. So you're more on the above 2 curves. Now, the cost curves we can assume to a good extent to be linear. So you see isolines, green and red, of cost. And what I varied here are the ratio of specific cost for generation versus storage versus generation. So the steeper ones, the green ones, is where storage is more expensive. And where now this, let's say, technical curve, separation curve, meets the cost curves, is the operation point of your system. And there you see that where you exactly are with your operation point of your future energy system very much depends on how the costs develop. I think that this blue curve, if we want, is more fixed and easier to predict than where we go with the cost. We can go one step further, because here I just talked about the storage, but in fact we understand that there are different types of storage, so battery type storage and chemical storage, like creating hydrogen or methane for that matter. And they are different in characteristics. So the battery storage is something that has a high return efficiency, much more than 30 or 40%, more in the range of 80%. But their energy and power are very tightly coupled. So you can store only, let's say, for a day, whereas for hydrogen, the power component and the energy component is completely decoupled. So you can have a very large storage that costs very little, and what is cost determining is the power component, so the electrolyzer and so forth. Yeah. So what you see here is the attempt to find out what the ratio between battery type and chemical type of storage, let's say hydrogen, will be in the future, depending on the ratio of specific cost for hydrogen and battery technology. And in this blue rectangle, we said this is a range of cost expectations that we would have for 2050. So it's still a large space here. So the master plan is not pointing to exactly one point there in the space, but it gives somehow a reasonable target area, if you want. And if you look on the scale, so this is normalized generation cost, they are not of equal scale. So the batteries are here on the space where we see a response is very much to very low battery prices. So if you look at the left chart, we come from the left, and long times there will be no stationary batteries at all in the system. Yeah? So if you come from the left. So this is what we wanted to find out. Does it make sense to put stationary batteries into the system? It's only once the specific cost for batteries go down very strongly that you suddenly see an increase on the relative proportion of battery power. Skip this. You can put these calculations further in, for example, trying to get an idea how the type of automobility will develop. We're starting from gasoline and diesel cars in this proportion presently. We are somehow slowly introducing hybridization cars for both of these technologies, and probably there will be a natural gas type internal combustion cars coming in, which can also be hybridized, range extended vehicle, plug-in vehicles. We don't see very much room for fuel cell type of vehicle. And then in 2050, we see that battery electric vehicles will be prominent. Yeah. In the total of Europe, we can somehow try to find out what different mixture rates between wind and photovoltaics are in the country. I said it yesterday that in the center of Europe, due to the climate conditions, there's a ratio of 1 to 3 for photovoltaics versus wind. And if you go farther south, Italy and Spain, of course, the photovoltaic fraction increases. And if you go farther north, like Norway or Sweden, then the wind and also hydro dominates. You can play the same games for India. And now let me come back to my original question. So is long-term planning socialism? Why is long-term planning so important? Because the assets that you're investing in, the backup power plants, the stationary batteries for that matter, and the generation types, they are all long-term assets. The payback times is 10 years, 20 years, sometimes even 30 or 40 years. And therefore, it's very important to have long-term planning in order to establish sustainable development and to mitigate the risks of the investment. One thing we also learn is we have to somehow include society or social impacts in these technical cost functions. Yeah, this is of course difficult to quantify them, but we have to try to quantify them. I said also the speed of change, let's call it the S-curve of macroeconomic development, is important, including the interconnections, coupling of time and climate zones relax the efforts. It's also important to understand that these minima where the optimum lies is not so sharp. Yeah? So they are usually quite smooth cost curves, and so you don't have to hit it in the 1% region. So plus minus 5% doesn't matter too much. The master plan, as I told, is a rolling planning, so you have to refresh your calculation every other year to keep track. And in the end, I want to make one technical comment, is I found that we have to go away from time series-based calculations and go to more stochastic, statistic distribution of events type of calculation. They are more robust, because otherwise you're so much dependent on this time series was taken in this photo year, and this is not the best way of reasoning. I hope I did give you this flavor of what it means to do long-term planning, put out some arguments. Hope you can get into a discussion about that. Thank you very much.
I think we can directly take one or two questions. Any question in the room? I have a lot of questions. I think I can discuss this topic for the whole evening with a couple of beers. Any questions from the audience? Yeah. Is there a microphone here? There should be a microphone in the room. The microphone is coming.
Hi, this is Ashish from ICF. I have a much more general question when it comes to planning and everything. I mean, we know that technology is evolving so fast. I mean, and the costs are dropping, like anything. So investment made today, I mean, would probably become, uneconomical tomorrow, and, the regulator or the purchaser might want to dump that contract. So how do you safeguard, or how do you basically factor that in the planning, and what's your view on that?
I hope it became clear on this one slide where I said that somehow we have to separate these technical parameters and the boundaries that they create from the cost, where these, and you saw that all the result pictures I showed, they were depending on the specific cost. Yeah. So now you have a reasonable assessment where this would be the operating point where we go if the specific cost would be there and there. And of course it reflects that there are learning curves that you have somehow to estimate. And I think a reasonable way to secure your investment is by what we had in this feed-in tariff, that you somehow secure the payback of that for the time of the investment. Yeah. So if you let everything free to the market forces, of course, somebody who invests at a higher price position for a specific technology is in risk at later times, because he has to sell his electricity for a high price. Yeah. So there's this intrinsic danger, of course, and you have, and this is a more subtle part of this planning, is somehow to understand how you can mitigate the risk. But I think that we are presently already coming into this asymptotic range of specific cost for the generation. I don't see that the risks are so high there anymore that you expect that they will still be half in the next 20 years. This is different to other technologies like batteries, which are still on the learning curve and still go down.
I just add developing countries' perspective in planning, long-term planning. My name is Anjana Das. I am working with Integrated Research and Action for Development. Here I add, for developing countries' perspective, why planning is important, because like demand is growing rapidly, And on the other hand, energy infrastructure takes a long time to build. For example, if you take the example of China and India, obviously they will depend on more, larger infrastructure like LNG infrastructure, nuclear power plant. So they take, 7-8 years to starting from project initiation to the actual capacity is available to the system. So from developing countries' perspective, I think planning is important.
I would just like to add 2 comments from my side. When I was a student about 25, 30 years ago, I had 2 professors. One was a professor who was an expert in wind turbine design, and another professor was an expert in energy planning. So they worked together, and the wind energy expert predicted that it will be technically impossible to build wind turbines larger than 600 kilowatt. And based on this definition, the energy planning expert concluded that Germany can never have more than 3 gigawatt of wind power, because he always calculated with 600 kilowatt wind turbines. So based on this long-term planning they did, you would never have predicted, or this development that you have seen in Germany would never happen. So I think long-term planning is very important, but it's very difficult to capture innovation. The second comment I have is to stranded investments. I think you have to accept stranded investments. We have heard this argument from the nuclear power industry and from the convention generator industry for a long time. And I think it's impossible to assume that you can do perfect planning. And I think a lot of companies who work in this field already are aware that the risk is much higher and that they might have to accept stranded investment at a certain point. And I think that should also go into the planning procedure, because if you would follow saying we have long-term investments which we have to make and we should not change it later on, then we still would have the same energy system that we had 20 years ago. That's my personal opinion.
It's also more a statement than a question, and I think I can fully support your argument. Just probably one criticism here. You should not hand the issue of long-term planning to technology people. Yeah, you should be, to some extent, be technology agnostic. Everything is possible technology-wise.
Okay. So there's a last question over there, then we have to continue.
Good morning. I'm Mehta from Gujarat Law Dispatch. So it's not a question, rather a view, and what I feel that when we do the planning of specifically any renewable or anything new, if we have foresight and we anticipate the impact thereof, like forecasting and balancing is a need with respect to renewable. But probably we miss that with respect to India or a state of Gujarat. So we feel that to be embedded things in a planning. Suppose I plan a 2000 megawatt renewable, then I need to plan it the same day, same time, the balancing requirement thereof as well as the forecasting need. Otherwise what happens that lot of problems are arising and we are not able to ripe the fruits which is to be delivered by the proper planning. Thanks.
I certainly think that some long-term planning has to be done, but I think it should be not too limited to maybe one scenario. I think what many companies do now who work in this field have multiple scenarios, and they try to basically look into what happens if scenario A, B, and C occurs, and how can we prepare for different scenarios. Because what they say now in Europe, what I have to be heard, is the most fluctuating thing in the energy field is not renewables, it's the politicians and the policy development, and that's a difficult part to adjust in your planning. Thank you very much.